Hello everyone, here is Elena Grigorieva and I'm a PhD student at the Chair of Communication Networks of the Technical University of Munich. In this video I'm going to present to you the automated map-based strategic fixed network planning tool, or shortly the AMS, and we're going to specifically talk about the motivation for this tool, the problem formulation and the generic description. Coming from the telecommunication industry perspective, we have the following problem. The requirements of the users are constantly growing. So users want to have more capacity, they want to have less delays, and this is what leads to the need of the fixed network operators to upgrade their networks to keep up with the users. Because, for example, if you think about the copper technologies, the early ADSL, 25 megabits per second per user at home now is not enough. Everyone wants to have, wants to be able to use the online gaming, to stream videos, and so on, not to say about the new applications. At the same time, the upgrade of the networks actually means for the operators significant investments. And as the user doesn't really care which technology in particular brings the connectivity to the home, the operators have to choose this technology and perform a so-called strategic network planning analysis. It is done basically from the motivation that the operators want to keep their profits, and the profits are the difference between the revenues and the cost. So normally you can either increase the revenues, reduce the cost, or do it at the same time. However, for the telecommunication operators, it is hard to increase the revenues because of the competition, regulation, and so on. So the operators want to find the best solution at lowest cost, and this is when they need this kind of network tools. What does strategic fixed network planning actually start with? So it actually starts with the area model, because it is very important for the fixed networks what kind of streets are there, how they are distributed, how the demands are distributed. Is it a city, is it a village, or this kind of information. And in the strategic phase, it goes in the direction of making a decision for the future. So it is not a very detailed plan about how to actually implement the network there. It's more about how much would it cost to implement this particular technology approximately in this type of the area. For example, a passive optical network in the urban area or in the rural, or maybe it is better to go with an active. So this kind of comparisons are the things that are needed in this phase, and they are very dependent on the area model. As you might know, the geographic maps are very heavy, computationally heavy, and very heavy data that really needs specific tools to work with, because they basically code every point in space in the information and also the relationships between them. So working with the geographic models is hard. This is why many of the strategic network planning was done based on the geometric models, which are the simplifications of the area based on the average area properties. As you can see, it has a number of downsides. The crucial downside for us is the unpredictable cost under and overestimations. So you cannot really use these results for business decision making unless your geometric model is very precise. This also highly depends on the actual area that you're working on, so it's not very reproducible. If it worked for Paris, you cannot say that it works for Munich. And this what makes it also unrealistic, not precise, and as it contains a lot of specific data to the network, they're not publicly available, so you cannot really use it. This is why we decided to go for the geographic models, because they provide more accurate cost estimation, they are reproducible, there are sources that you can use as OpenStreetMaps, and they're based on the available online data. So how do we go with it in our AMS Planning Tool? We use the Geographic Information System, ArcGIS. The reason for that is, I mentioned before, that the maps are very computationally heavy, and as handling this kind of data was not our primary objective, we decided to use something that is already implemented and widely used. We also look into the real estate topologies from OpenStreetMaps. The implementation is Python based, and it has ready-to-use tools with easy GUIs, because ArcGIS has a lot of pluses when you use it with the maps. You can do there a lot of analysis, but it is not very beginners friendly, and some complex analysis you'll have to work in yourself for quite some time. This is why we decided to do a user-friendly tool that actually doesn't require any Python knowledge or any ArcGIS knowledge other than superficial, so that you can load there the data. So what our tool actually is able to do. So we have different options of the planning that could be carried out. So we have different topologies. We have point-to-point and point-to-multipoint. The point-to-multipoint, we have also single stage, that is with one aggregation point in between, and with more stages, that is with more aggregation points in between. And we also have different types of clustering, that is how the demands of the aggregation points are grouped together. So we also work with different endpoints, with homogeneous. For example, if we need to connect only the residential users or only the base stations, and heterogeneous, when we connect everything together, and this is what is called converged planning. We also look into protection, so of course you can do it unprotected, or you can do the protection, the shortest path link disjoint protection, or encouraging duct sharing link disjoint protection of the feeder fiber. The reason why it's not only for feeder fiber in the access network, because normally it would be cost prohibitive to protect anything else, as also the impact of the failure is fairly low. So talking about the architectures, we support the following fiber to the X architectures, where the X stands for the fiber termination point. We support the fiber to the cabinet, that is that the fiber goes to the cabinet where the optical network unit is placed, and the rest is assumed to be connected with existing copper. As in our planning tool, we don't know how the copper is placed. We do the planning as the network operators would do it. So we also then first do the planning for the copper with the cutoff. And the cutoff here means that the copper links cannot be longer than 500, 1000 or 2000 meters, because the capacity drops dramatically with that. And then when we know from that, we know the distribution of the cabinets, and we can do the actual fiber planning. We also have the fiber to the building, where the fiber is terminated in the building, and in the building itself we assume that copper is there. And also it could be fiber to the home. Right. The architectures that we support here, this would be protected point-to-point connection, where we would have working fiber and protection fiber. This is normally, as shown here, would be used for the macro base stations. The fiber to the building, single stage, so this is the only aggregation point. This is also what is implemented, and of course the fiber to the cabinet is then a two-stage aggregation network. In this case, all of the demands are homogeneous. So this is not converged planning. Converged planning looks something like this. We have here two stages. And as you can see, we have a number of demands. So we have the residential users, we have small cells, we have macro base stations, and the difference between these two architectures is that we can connect the small cells as the time division multiplexing together with the residential demands if they do not need a high capacity, or we can also connect them as the VDM, wavelength division multiplexing demands if they need more capacity, for example in the 5G case. This is also something that can be done. So finally, the planning itself. Let's summarize what are the inputs. So we have the city street topology. This would be the OpenStreetMaps. We have the central office location. Normally it's placed or known. We have the demands. They could be homogeneous or heterogeneous, and possibly remote node locations or aggregation point node locations. They're normally the intersection or any other points that are reasonable for your case. And we also have the access network parameters, that is the number of stages, the splitting ratios of the aggregation points, that is how many demands can be connected to one aggregation point, and also if we need protection and so on. So what do we get as the output? We get the remote node locations and the fiber layout that aims at minimizing civil works. You can see that this is why the civil work is quite costly, and we later show that it's indeed the cost driver in this case. This kind of results can be used in the analysis of the cost, the availability, and the delay. So the methodology of this planning follows closely the methodology presented in this paper from my supervisor. First we are doing the clustering, so we are assigning the demands to a remote node, and we're placing the remote node. This is done as a allocation problem with capacity constraint, which is actually already implemented in the ArcGIS. The cluster head then defines the remote node position, and it is performed for every stage of the network. In some of the cases we use the cutoffs when it is necessary. That is, that no links can be longer than specific distance. The routing afterwards is done with the shortest path routing, which relies on the street topologies and not on the Euclidean distances. In fact, it's a Dijkstra algorithm that is also already implemented in the ArcGIS. The outputs, as was mentioned already, are the remote node locations and the fiber and duct length. This, as also mentioned before, is the input for cost and availability, and further analysis examples of that we will show later. So we'll start with one example of the results visualization from the paper that is now being under revision. So this is how the input looks like. We have our central office. We have two types of demands. In this case, these are roadside units, which are basically these small cells for intelligent transportation systems. We have the buildings, and we have the public transport routes where these small cells are placed, and then we have the streets. We did the planning for these two groups separately and together to save the energy, but if you're interested you could then refer to our paper. And this is the kind of output visualization that you get here. So you have the central office, you have your remote node 1, you have your remote node 2, you have the feeder fiber, it's without protection, and you have your last mile fibers in this case for all of these clusters. The same is also here. For the cost analysis, you can see that the duct costs are dominating the entire costs, and this is why we also concentrate on the duct minimization. This is an example from another already published paper. Okay, this concludes my presentation. Thank you very much. There are also individual videos on the use of the individual tools. Have a nice day. Bye.